So yesterday you were watching a video about logs and switching forms with logs and all that stuff. I just wanted to draw your attention to the fact that if you have the same base, so if your log and your exponential have the same base, then they just cancel each other out. Okay? So for instance, in number 7, okay, in number 7 we have a base of e on our exponential term, and we also have a base of e in our logarithmic term, which is in the exponent. Okay? So because they're there, these two just cancel each other out, and we're left with this is just 5. Okay? If I look at a logarithmic type 1, okay, like number 4 or number 6, first off, I could write this as log. When there's no base written, we're assuming that that means log base 10. So if I'm thinking about that, 100 is 10 squared. Okay? So this would really be log base 10 of 10 squared to the 1/7 power. So those two right here, this 10 cancels out that 10, and so then that just leaves me with 2 to the 1/7 power. Actually, take that back. It's not 2 to the 1/7 power. I correct myself right away. Whoa, tap the brakes. That's supposed to be an eraser. It should be 2, because it's power, that means you multiply, times 1/7, or 2/7. Right? We're going to start doing some log stuff today. We're going to be basing it off of your prior knowledge. Okay? So we're going to go fast today. If you have questions, come into the resource center or stay after class, and we'll get them answered. Okay? All right. So we're solving logarithmic equations. Now there are two different. I shouldn't say different. There are two methods. There are two methods to solving logarithmic equations. One method is you could look and see what the base is of your log. So in this particular case, it's log base 10, and so you could take both sides and put them in the exponent spot of that base. Okay? That's method number 1. You could take it and you could do that. Okay? What that does is what I was just talking about. Now the exponent, or excuse me, the base of the exponential term is the same as the base of the logarithm in the exponent, so those just cancel each other out, and then we get x equals 10 to the negative 2 power, or 1 over 100. Okay, that's one method. Little complicated. It's a little, there's a little bit of extra stuff in there, but you don't have to memorize anything. You just take both sides and put both sides in the power of the base of the exponent. Okay? The other method that we have is, I'll go way up here with it. The other method that we have is you got to memorize the fact that it's log of the base of the argument equals the exponent. That's the same as base to the exponent equals the argument. Okay? Which you learned last year in your algebra class. Okay? So you can switch forms with it. So here again, my log is log base 10. So 10 is my base. Negative 2 is my exponent. x is my argument. It goes right to it, right there, and so then we just get the fact that x is 1 over 100. Okay. A couple of different ways to solve them. Okay. Log base 2 of x equals 4. If I do it the first way, now I would take 2, log base 2 of x equals 2 to the 4th, and this left side just cancels everything out other than the x, and 2 to the 4th is 16. If I do a change of forms method, then 2 would be my base, 4 is my exponent, x is my argument, 2 to the 4th is 16 equals x. Okay? I don't care which method you choose. I really don't. All right? You now take a couple of seconds here to solve 3 and 4. Either method that you did these in, this one should have given you x equals e cubed, okay, which is somewhere in the 24-ish range, I want to say. I don't know, did anybody actually calculate it out? E cubed? Okay. I mean, it's so much cleaner than 20.085. Okay. This one should have been x equals 10 to the 1/2 power, or I would also accept the square root of 10. Okay. But I'm also okay with x to the 1, or excuse me, 10 to the 1/2. Questions, comments, concerns, clarifications? All right, let's do this. Here we go. All right. So we graphed exponential functions. We graphed them last week, Friday. We graphed them with base E this past Tuesday. Okay. So today, now, let's refresh our memory with graphing an exponential function. So first off, when I got the graph of an exponential function, I'll put it here in green. I've got a horizontal asymptote of y equals 0. I've got a function that is growing much like this. The domain is all real numbers, because any x I can put into that function. My range is all real numbers greater than 0, so I could just say y is greater than 0. Okay. And my y-intercept is going to be at 0, 1, right? Or if we had an a in front of it, it would be at 0, a. Right? Agree? Logarithmics are the inverses of exponentials. Does anybody remember from Algebra 2 what it means to be a true inverse function? Other than it cancels each other out. Like addition cancels out subtraction. Multiplication cancels out division. Logs cancel out exponents. Does anybody? Let me refresh my question. What do we do in a true inverse function? What changes? What changes in a true inverse function? x's and the y's switch around, right? Okay. In a true inverse function, your x's become your y's become your x's. So we flip-flop those. Okay. So if that's my graphically, that is my exponential function. Okay. The inverse function then would be, so now my domain, that was my x's, right? That's a bad x. My range was my y's. So that means those are going to switch, correct? So now my domain is not going to be all real numbers, but my range is going to be all real numbers. My range, instead of being y is greater than 0, now that's going to become my domain, and so it's going to be x is greater than 0. My horizontal asymptote at y equals 0 is going to change to a vertical asymptote at x equals 0, yes. Now, instead of having a y-intercept, because all y's become x's, now I'm going to have an x-intercept. Where is the x-intercept going to be? Say it louder, Ed. 1, 0. Exactly. Okay. So if I put that on now I've got that, my vertical asymptote at x equals 0. Now I go through the point 1, 0, so my function, the graph of my logarithmic function is going to be that in blue. Still looking for the two easy ones. Okay? The two easy ones are where your exponent, logs, okay? You can write this down if you want. Logs are exponent finders. Logs find exponents. So I need to find where an exponent is going to be 0 and where an exponent is going to be 1, because those are my two easy ones to plug in for my graph. Okay? I don't think there was one down here. Where did my what in the what in the what? Why can't here must not be. No, must not be. I thought I need to get that scroller on this side. There it is, and then it just goes away. All right, so if I've got y equals log base 10 of x, the 2 that I'm looking for is I want to get an exponent of 1, and I want to get an exponent of 0. Okay, well, ten to the first power, right, would give me that one. 10 to the 0 power is 1. So that would go through those 2 points right there. Okay. So on a graph, I would go through 1, 0 and 10, 1. So I would come up, scroll through there. I would still have a vertical asymptote at equals 0. Natural log, y equals the natural log of x. Again, I'm looking for a y value here of 1 and a y value there of 0. Okay? So to get the 0, I need that to be 1, right? So that's going to just be 1 comma 0. E to the 0 power is 1. Okay? E to the first power is 1. So I would go through 1 comma 0 and then 2.7-ish comma 0. So there would be there, and then we would have our vertical asymptote there of x equals 0. Okay? Love it. There are 4 properties of logs that you learned back last year, and I know because I just talked to Jay Crew this morning when we were talking about this, and he's like, oh yeah, we went over those. And Schmelling's like, yeah, regular, we went over these hardcore, so I know that extended went over them hardcore too. Okay? We use these properties in 2 ways. In the first way, we use them for expanding and condensing logs if we need to do those, and then that allows us to use it in the second way when we're solving problems with multiple logs in them. We need these properties. Okay? So the first one is the product rule. The product rule says that if I have 2 products that are being multiplied together, I can break that log up into 2 different logs. Or if I have a number, like let's say 6, I can break that up into 2 times 3. So I can break those up into 2 different things. And then that would give me the log base b of u plus log base b of v. Again, works both ways. So if we're solving a problem and we have 2 logs on the same side that we're adding together, we can condense them down into 1, provided that they have the same base. These properties do not apply if we have logs of different bases. Okay? The quotient rule, well, we switch from multiplication to division, so that means we're going to switch from addition to subtraction. Okay. Again, both of those are going to be primarily used for us in terms of solving, to condense down to 1 single one. Power rule is phenomenal. The power rule says that if you have an exponent on your argument in the log, that we can take that power and we can put it out in front. We can just multiply the log by that power. It's an offshoot of the product rule. Okay? Because if we have u times u up there in the product rule, well then that's log base b of u plus log base b of u, so you've got 2 of the same things. If you've got 1 pencil and I give you another pencil, you now have 2 pencils. Okay? So then it becomes 2 times log base b of u, which is the same as u times u is u squared. Okay? Truthfully, the real of the four formulas that you are going to use the most is going to be this last one, the change of base formula. Okay? Now, if you have a fancy calculator, and by fancy calculator, I mean one of the TI Inspires, or I believe that the Casios do these. Okay? The TI regular ones, the TI 30s that I see all around, those don't. Okay? They're not fancy. Sorry, those are basic. Okay? Right? But the TI Inspires and some of the Casios have, when you type in the log, you can type in a different base for yourself. And then you can type in the argument. But for those basic type calculators, you can't do that. And so the change of base formula is, now we do it in one of two ways, okay, is log of u divided by log of b, or the natural log of u divided by the natural log of b. Okay? There'll be posts on Canvas too. If you pick up the video at 21 minutes and 30 seconds, that'll be where you left. So there's that. Okay? Because it's not always easiest. Your calculator only, again, is basic. That those TI Inspire ones are basic. They are not the TI Inspire ones. The TI 30s are the basic ones. And they didn't want to program them in with multiple bases. So they just picked base 10, common logs, and natural logs. Okay? We'll get into this here momentarily, but so if I was doing this, I would say log base 2 of 7. Again, logs are exponent finders, right? Okay? So I need an exponent to go on to 2 to give me 7. Well, it's got to be bigger than 2, right? Because 2 squared is 4, but 2 cubed is 8. So it's got to be somewhere between 2 and 3, probably closer to 3 because 7 is closer to that. So then I would do here, now, that would equal either log of 7 divided by log of 2, or natural log. It really doesn't matter which one you use. You're going to get that either way. Natural log of 7 divided, oops, I gotta close my parentheses too, divided by the natural log of 2 gives me 2.807. It allows us to evaluate what exponent. So if I put an exponent of 2.807 onto 2, it's then going to give me 7 as an output. Okay. Love it. Here we go. So let's expand some logarithms. I'll do one, then I want you to do 3 of them. Okay? So we want to expand these logarithms. Okay? By expanding, that means we want to get to multiple logarithmics. Okay? So if I'm looking at this one, this would be the log of 100 plus the log of x plus the log of y to the 5th power. Because all of those are being multiplied. 100 times x times y to the 5th power, those are all products. Okay, so we're going to expand it out with addition. Well, then I can go even further, and I can say here that log of 100, what exponent do I need to put onto 10 to get me 100? 2. So this one simplifies to be 2. This one doesn't simplify at all, so it's going to stay log of x. This last one, I can apply the power property, and I can say that that is log, or 5 log of y. And that, ladies and gentlemen, is the expanded form of that one. what I would like you to do now is I would like you to expand the other 3. Go. Those are what I got for my expansions. Questions, comments, concerns, clarifications, need me to go through any of them? One might say, speak now or forever hold your peace. Okay. Going back the other way then, here in our last 3 minutes, okay? Coming back, now we're condensing into 1 log. So now what I've got to do is I've got to do all of those properties, but in reverse. So the first one that I'm going to apply is I'm going to apply the power property in reverse. So that becomes x to the 1/2 power. Then this still becomes minus log of y cubed. Then I can combine those both into 1 single solitary log of the square root of x divided by y cubed. Technically, I should put a set of parentheses around those. Here on number 2, natural log of 2 minus natural log of x is going to be the natural log of 2 over x. I don't like how I wrote that one, so I'm going to quick rewrite that. Oops, I missed it. But then I still have got minus the natural log of y cubed. Well, subtraction, does that put it on the same level or does it put it below? Puts it below, so that means it's going to be on the bottom of the existing fraction. So that means that this is going to be the natural log of 2 divided by xy cubed. This one would be, in the end, we would have natural log of, we would have x to the 5th on the top, we would have y squared on the top, and we would have the square root of z on the bottom. This one we would have the log of the 3rd root of 5x on the top. We would have y to the 4th on the bottom because it's being subtracted. And we'd have 3 squared, which is 9 on the top. So I'm going to throw a 9 out in front there. Okay? Have yourselves a great, grand, and wonderful day.